we have an object sitting on an horizontal surface. And the purpose of the game is to identify all the forces acting on the system, specifically the normal force. Let's imagine that we are given the mass of the system. Okay, so clearly we're looking for the magnitude of the force, which implies that Newton's analysis is the most adequate. Keep that in mind, because as we're going to build up concepts on top of each other in a couple of months, it may not be as clear about which method you want to use. But make the association. Okay, whenever I'm looking for a force, Newton involved forces, so the force is equal to ma. We went through the first, second, and third law last time. Therefore, most likely, I need to apply Newton's either first or second law. So the first step in the method is to identify our system. In this case, it's trivial because there is only one, but in more complex situation, we're going to have more than one system. And identifying the system will imply the results of the subsequent steps later on. So it's very, very important not to skip the first step. In this case, we only have one object, that's the block, easy. Second is to identify all the external forces acting on your system. All the Newton forces must be contact forces, and they must be external to your system, and they must be acting on your system. If you memorize the definition, you can never go wrong. The only exception that we're going to be facing is the weight. That's the only force that acts at a distance. The reason for this is the weight is technically not a Newton's force. It's a simplification of a gravitational force, which is a fundamental force. So Newton forces are all contact forces. They're all external to your system, and they're all acting on your system. The list is given to you on the FAQ. There are going to be 1, 2, 3, 4 types of forces. The first one that comes to mind is the weight. So let me write down on the side list of forces that you can choose from, and I'm going to write them in order. I would strongly suggest that as you apply Newton's law, you go through the same order, because a common pitfall is either to invent or to forget forces. So the first one is the weight. We write it as W. That's the force due to gravity. Weight and force due to gravity are the same thing. We're going to see that specifically in chapter 13. So for now, we take it for granted. That's a force that acts at a distance. That's the only exception with respect to contact forces. And the nice thing about this weight is we know its magnitude. It's going to be the mass times the acceleration due to gravity that we've seen in chapter 4. As I've pointed out many, many times, G is always positive. Gotta be, since it's part of the definition of its magnitude. So mg is always positive. We also know its direction. It's always down. So that's the nice thing about the weight. If you're given the mass, you always know everything about this force, its magnitude and its direction. Second, the normal force. We usually write it as capital N. This normal force, we never know its magnitude when we start a problem. Ever, 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 ever. So never assume the magnitude of the normal force. That will make your life easier later on when the system is more complex, that involves more than one system, and when the surfaces are not horizontal. So don't take the habit of guessing the normal force magnitude. We will always obtain the magnitude by solving the equations. However, we know something about its direction. Its direction is always perpendicular to the surface. So a normal force pops up every time that your system that you have identified in step 1 is in contact with another system or a surface. And we know that the direction of the normal force is always perpendicular to that system or that surface, and is always acting on your system. All right, so make sure you take good notes. Those are the fundamental definitions and property of those forces that will be useful for this class. For the next class, C270 if you're CNME. For the next class for CNME, such as C271. The next one in line is any force that push or pull. Usually either the problem gives it to us orally or they give it to us visually. So usually those are given to us. For example, the force due to spring may be one of those candidates. That's a force that either pull or push our system. So any pulling or pushing. And the last one is going to be friction. So only 4. I'm going to leave friction out this week. I'm only going to introduce friction next week. That's chapter 6. So for now, we are only considering the first 3 of the list. Very easy. Okay? So again, 4 forces. First one is the weight. We know its magnitude. It's mg, always positive. Obviously, its unit is Newton. Mass is kilogram. G is meter per second squared. Therefore, units of W is kilogram meters per second squared, which is the same thing as 1 Newton. And we know that its direction is always downward. The second force that comes to mind shows up every time that your system is in contact with another system or surface. So there could be more than one if there is more than one contact. We never know its magnitude, but we always know that this force is perpendicular to the surface or the contact and is always acting on your system. The third type is any pushing or pulling. That's where the spring force may be showing up if there's a spring involved. And the last one is friction. And we will go more into detail on friction later on. So I'm going to leave it for now. Okay, so in this particular case, we have a block sitting on the horizontal surface, and we will have to figure out all the forces acting on it, specifically the normal force. So the first thing that you want to do is, after you have identified your system, let's identify all the external forces that act on our system. Let's go through the list. Obviously, we have the weight. The weight is usually drawn from the center of mass of your system, which we'll see in chapter 9. Always down, always positive. So I'm going to use an arrow pointing down with the label W. Second one is their normal force. Obviously, our system is in contact with the surface, which is horizontal. Therefore, there must be a normal force whose direction is perpendicular to that surface. Therefore, that normal force in our case is vertical. The question is it vertical up or is it vertical down? To figure that out, we use the second part of the definition, which is that this normal force always acts on our system, because all those forces must be external to our system. Therefore, in this case, N must be acting on our system and therefore must be going up. And it's located at the contact between your system and the surface. Third, is there any pulling or pushing? Nothing is being specified in any one question about any pulling or pushing, so we have nothing. And then we have no friction yet. Friction, you will know if it's present if you're given the 2 coefficients μk and μs. In any one, none of those 2 are given, therefore we don't have to consider friction. That's it, only 2 forces. So the next step now is, once you have identified all the external forces, is to complete a free body diagram. A free body diagram is a diagram that includes all your forces with the label, a coordinate system, and then all the direction of all the forces with respect to your coordinate system. And you can pick any coordinate system that you like. The nice thing about Newton in chapter 5 and 6, when we only do translation, is that you can always represent whatever system you're dealing with that has any shape with a 0-dimensional point. We're going to lose that nice little simplification in chapter 10 when we start doing rotation. But until then, we can replace whatever complex shape our system has by a 0-dimensional point. Since vectors are vectors, they have 2 properties, magnitude and direction. The nice thing about vectors is we can move them around. As long as we don't change neither the magnitude or the direction, they're the same vector. So I'm going to draw all those vectors from the 0-dimensional point that represents my system. Hence, I'm going to have W here and N here. two forces. Now let's pick a coordinate system. Remember, you can pick any coordinate system, X and Y. If your system is at rest, like it is in NA1, it means that our system is not accelerated, which implies that Newton's first law can be used. So if there is no acceleration, the trick to pick the coordinate system that will make your life the easiest is to choose either the X or the Y axis, such that any of those two are aligned with as many forces as possible. And you understand that because of chapter 2. If all your vectors are along your X and your Y, expressing them in component notation is a piece of cake. So in this case, they're both vertical. So sure enough, I'm going to pick one of my axes, say the Y-axis, along those two forces, and X perpendicular. We're almost done. That's the second step of a complete free body diagram. The third step is to identify all the direction between every one your vector and, whoa, either your X and your Y-axis. In this case, the direction is trivial. N is along the Y, positive. W is also along the Y, negative. Therefore, no need. You only have to figure out the direction if your vectors are either in the first, second, fourth, or third quadrant. Done. Now that we have all this, this is the core of Newton's analysis. That's where all the science is. After that, it is just back to chapter 2. We have a bunch of vectors in the coordinate system. We know Newton's first law, in this case, will ask us to add those two forces because there is no acceleration. Therefore, A is 0. Hence, we already have to add them up. And we've seen from chapter 2, the way to add them up is to express them in component notation and just add them up. So, the intermediate step, if you need to go through this at the beginning, is to first express each of those vectors in component notation, because we know we're going to have to add them up. So N obviously is 0 and N. W is 0 and negative mg, because it's down, and our positive y is up. Therefore, as we express this Newton's first equation, we end up with N plus W is equal to 0. That's Newton's first law in vector equation, or vector notation. Now let's just add them up. This is obviously a two-dimensional problem, x and y. We don't have to deal with the z. Therefore, a vector equation will give us a system of two equations. You add all the x components together, and you add all the y components together. Those two are equivalent, 1 and 2. And now all you have to do is plug the numbers. Nx is 0, wx is 0, so the first equation gives us nothing new. The second equation gives us n minus mg is equal to 0. It is that simple. That's how the Newton's method works, and that's it. Now we just solve. We have a system of two equations to unknown. Obviously, the normal force can be expressed as just a weight. So in this particular case, the normal force happens to be the same as the weight in magnitude. But do not memorize this and use it here, ever. Because it's a very simple case. You're never going to ask that on any test. Okay? We obtain the magnitude naturally from the equations.